Hi, thank you for coming right after lunch. So let's see, I'm Rich Caruana, Yin Liu. This is a lot of Yin's PhD thesis at Cornell is sitting here. And this is joint work with Johannes and Paul Koch, who are both at Microsoft, and Marc Sturm, who's at New York Presbyterian Hospital, where we got some of the data, and Noemie Elhadad, who's at Columbia. Okay, so let me just jump in. I give you data for 10 million patients. I give you thousands of great features. You're really good at machine learning. You train a state-of-the-art model on this data, and you get phenomenal AUC, right? You never really get 0.95, but you get 0.95. Okay, so everything is looking great. Now the question is it safe to actually deploy this model and use it on real patients? Is high, unbelievable accuracy on a test set sufficient to deploy? And I think I'm going to show you that no, accuracy is not sufficient, specifically on a test set. So let me jump in. This is what you've got. You've got this black box. It's incredibly accurate, but you don't know anything about what's in this box. And there are gremlins in the box that will hurt you, or even worse, they'll hurt patients. So let me show you how that can happen. 25 years ago, I was involved in a study where we were trying to predict pneumonia risk, probability of death from pneumonia. And we were looking at a variety of machine learning methods, logistic regression, k-nearest neighbor, neural nets, things like that. This was a long time ago, so we didn't really have SVMs and boosting and random forest yet. And I got lucky. The model I trained, the multitask neural net, turned out to be the most accurate model that any of us could train on the data. And then the question was it safe to use this neural net on real patients? We were thinking about doing a clinical trial. Was it safe to use this neural net? I convinced them not to use the neural net, and instead we used logistic regression, one of the poorest performing models on real patients. So the question is, why did we do this crazy thing and not use the most accurate model and instead use one of the least accurate models? Well, let's see. So the goal of this study was to predict your risk of pneumonia. And if you're low risk, we're going to not admit you to the hospital. We're going to give you antibiotics, chicken soup, and you should call us in 3 days if you're not feeling better. That's actually very good practice for pneumonia for most patients. But if you're high risk, we definitely will admit you to the hospital. And in fact, 10 to as much as 15% of pneumonia patients die of pneumonia. If you're high risk, you really do need to be in the hospital. One of my colleagues was training a rule-based system on this, and he learned the rule that if you have asthma, it lowers your chance of dying from pneumonia. You don't have to know a lot of medicine to question whether that rule makes sense. So at the next meeting with the doctors, we brought this up, and they said, oh, that's very interesting. It's probably a true pattern in the data. They said, asthmatics who present with pneumonia, we consider them very high risk. We not only put them in the hospital, we often put them in the ICU, and they get very aggressive care for their pneumonia. And the good news is you're telling us that treatment is so effective that it actually lowers their chance of dying compared to the general population who doesn't get that aggressive treatment. So that's great news, right? Chalk one up for healthcare. The bad news is we were training a model to try to decide who to admit to the hospital or not. This model thought that asthmatics were low risk, so it would tend not to want to admit them to the hospital, which is the exact opposite of the care that they should receive. So presumably this model, if we deployed it, or any model that learned this pattern, if we deployed it, could put asthmatics at risk. Now, we're smart people. We all do machine learning for a living. We probably could figure out a way to prevent the neural net from learning this. The rule-based system, it's easy. You just take the rule out. The neural net, we probably could figure out how to get this out of the neural net. I won't talk about the tricks for doing that because it's not what we did. But the one thing I want to emphasize is you're always going to have this kind of problem because it's not ethical to collect data that doesn't have this problem, right? It's not ethical to collect a data set where you didn't treat asthmatics the proper way. So you're always going to have this problem. And it'll turn out you can't just sort of remove asthmatics from the data set for reasons that I'll talk about later. Okay, so the key problem is not really the asthma problem, because once I know about it, I can probably do something to mitigate that concern. Maybe I could just say, never use this model on asthmatics. Train a separate model for asthmatics, something like that. The problem is, what else did the neural net learn that's bad, like asthma, but the rule-based system didn't learn it, so I don't know that there's a problem? For example, just suppose that pregnant women who have pneumonia also receive very effective aggressive treatment, and that lowers their chance of dying, maybe the model would predict that pregnant women were also at low risk, and then we would withhold care from them. So that would be a bad thing. The key to discovering this asthma problem was the intelligibility of the rules, the fact that we had an intelligible model that had learned this. The neural net is more accurate. Presumably, it learns things the rule-based system never learned, which is why we wanted to use it. Unfortunately, the neural net is a complex model. We don't really know how to open it up and sort of understand everything it's learned. So that really kind of makes it risky to deploy this neural net model because presumably it could have learned other things that are bad and might hurt some classes of patients. The bottom line is you really have to be able to understand a model before you're going to deploy it on some apps in healthcare. So let's talk about that. We've made some progress now. This has bothered me ever since this happened 25 years ago because it made it look like the most accurate machine learning methods that we have, things like boosted trees, random forests, and neural nets, it looked like maybe it wasn't going to be safe to use these in healthcare. So we were going to have to throw away high accuracy in order to retain intelligibility so that it was safe to use the model. So the good news is we've made some progress on this, and we've got models now that are very intelligible, but they're also very high accuracy. So that's what we're going to talk about. So let's talk about the space of models. The simplest models are things like linear models, good old logistic regression, just a weight times a feature, right? Very simple additive model. The most complex models are things like random forests, boosted trees, neural nets, deep neural nets, things like that. These models are often more accurate than these models. Unfortunately, they're usually very unintelligible. The good news is there is a space in between these things. So a simple additive model, unlike a linear model, what we do is we still have an added sum from a bunch of terms, but it can be a complex function of the feature for each of these terms. So instead of being a weight times a feature, it can be some complex, nonlinear, multimodal function of this feature, and then you can have another complex, multimodal function of the next feature. So you have functions that are complex functions potentially of individual features, and then it's just an additive sum of effects. So that's a very nice class of models, as I'll show you in a few minutes. We can make that more complicated. So this summation over the single features is this additive model. We have functions of individual features. This is summation over all pairs of features. So this is modeling pairwise interactions between features. And then we can model three-way interactions between features. And in fact, if you have n features and we go all the way up to nth order features, this class of models can represent everything that's possibly learnable. Now, of course, we'll never go all the way up to nth order interactions. And in fact, what we're going to do is we're going to stick with the function class, which is either linear features, okay, so this is functions of single features, or functions of single features plus some, functions of pairs of features, pairwise interactions. We're going to stick with that class, and hopefully I'm going to demonstrate to you that that's actually a fairly intelligible class. And surprisingly, we can get a lot of accuracy out of it too. So that's where we're going. We did not invent these. These are called generalized additive models, for those of you with background in statistics. These were invented 30 plus years ago by very bright statisticians. There's some very nice literature on these things. What our contribution is going to be really just two things. We're going to put full machine learning, computer science horsepower behind these models. So we're going to fit them very, very accurately. We're going to get as much juice out of them as possible. And then we're going to show that if we're careful, these things remain intelligible, that they're intelligible models. So that's what we're going to do. Okay, I'm just going to sketch the algorithm. It's actually quite simple, and it's in previous KDD papers that we've written over the past 4 or 5 years. First, what we do is we build the most accurate additive model that we can, where we get to shape individual features. So if there are n features, there are n terms in this model, we get to shape each one. And we do this behind the scenes with some complex boosted decision tree process, but I won't go into it. So basically, we build this complex additive model with all these shape functions of individual features. We freeze that. If we've done that perfectly, everything that's left when we calculate the residual has to be pairwise interactions. That's all that can be left, if we did this perfectly. Of course, we never do it perfectly, but if we did, we would only have pairwise interactions left. Then we have a fast algorithm that we published a few years ago for finding the most important pairwise interactions. We're actually able to scan all n squared pairwise interactions, very quickly determine the few that you should keep in the model. And then what we do is we do a process just like this to now build shape functions that are shapes of the strongest pairs. And I'll show you some of those pairs. So then we shape those. These are all being shaped together. And then what we do is repeat this process with bagging maybe 10 or 100 times, and that's to give us sort of pseudo-confidence intervals, so that when we're looking at the graphs, you're able to see what's important. Okay, so 2 data sets. The pneumonia data set, I actually got permission to go back to the original 95 data set. It's a lot of fun to revisit a data set you spent years working on. And then we have this modern, this is predicting probability of death. This is predicting 30-day hospital readmission. So this is a very, very different data set. This is all cause. We've got hundreds of thousands of patients here, and we have 4,000 features. And I'm going to show you some results on both of these data sets. Just to give you an idea, logistic regression is not a bad model, especially if you're careful to Booleanize the continuous features in the right way so that you can get the maximum benefit from all those features. So logistic regression does pretty well if you do that Booleanization, that quantization of features correctly. Our GA2M models, this is our models with pairwise interactions, does extremely well. It does better than logistic regression, as you might expect. And I think the most important thing is it does as well or better than other things like random forests and boosting. So it's a very high-performance model. In fact, in healthcare data, we find it does as well as anything else. There are other problems, say, in the UC Irvine data set, where we only get maybe 90 or 95% of the accuracy that you would get with a full complexity model. And that's because things like 5-way, 10-way interactions could be important in a robot joint arm problem or something like that. But on most data sets, in fact, we are achieving almost the same accuracy as a full-blown boosting random forests and neural nets. Okay, so it's a very high accuracy model. The most exciting thing, though, is what it does to the features. Now, the shaping that happens mainly happens on continuous features. So in the pneumonia data set, we have a number of continuous features, and I'll show you what it does. On the Boolean features, it's essentially logistic regression, which is a good thing. So let's jump in. This is age in the pneumonia data set. So we're predicting risk as a function of age for that data set. This is being learned in parallel with the learning of risk for all the other features, so it's not just learning this independently. And the way you read this is, if your age is 30, you go up here and you subtract minus 0.28 from your score. So you have a score that starts at 0. If your age is 70, you add 0 to your score. If your age is 80, you add 0.18 to your score. Okay. So you have one of these graphs for every feature. It's been learned from the data. It knows nothing about what these features are. And then for each value of the feature that happens to fit a patient, you just read off the graph the score that you add. And the way these scores are done is, if we add +1 to your score, roughly speaking, it doubles your probability of death. And if we subtract 1 from your score, roughly speaking, it cuts your probability in half. These are essentially log odds. And then we sum this over all of the features. You'll see more features in a second. And then we calculate your probability of death. Let me show you some detail of this. First of all, it's good to be young. The model basically says if you're 48 and below, that's great, low risk, right? Or it's a really good thing. Your risk slowly increases once you sort of hit 50-ish. Then there's a spike in this data set. Remember, this is an older 25-year-old data set. There's a spike that occurs just after retirement age. Now, there's nothing about retirement, so let's just learn this from the data. There's a spike, an increase in risk. You know, you might have thought that retirement would lower your chance of dying from pneumonia, but it doesn't seem to be the case. So there's a jump there. Then your risk rises rapidly with increasing age, which I think you might expect. There's another spike, which is interesting, at age 86. We're not 100% sure what causes that. One interpretation of this spike is that, especially in an older data set, you know, if a patient is elderly, 86, 87, 88 years old, and they've already had 2 rounds of antibiotics and they still have pneumonia, you might decide not to treat. You might decide, look, the patient is elderly, obviously things are going bad. We might decide not to treat. But you might make that decision differently if the patient was 82 or 83. So this might be a social, there's certainly no written rules in the hospital that would cause that to happen. But it might be a sort of social convention in healthcare. And it's not just doctors necessarily making this decision. It could be family members making this decision as well. And then risk seems to be surprisingly flat as you're above that age. And then there's a spike down. Now, the error bars are very big here. We have very few samples out here. We don't know if this is real. In fact, I would guess it's not real. But surprisingly, we see it on another data set. And some people have suggested, David Heckerman suggested, that this represents successful agers, a very small group of the population who actually have genetic traits that make them age well. So, okay, so here's the interesting thing about this model. I assume if we had trained logistic regression, if we had trained random forest or some complex model, it would have learned something equivalent to this internal to the model. But we would never be able to sort of look at it and see it and understand that there are these jumps in the model, right? But this is the model. There's nothing hidden in our model. This is exactly how you make predictions. You go to this graph and you read off a value. Okay, so let me show you. Statisticians would have just trained a linear model for age, so instead of this complex model. And I think in general, statisticians tend to be a little conservative, and that's why their ROCs aren't as good as we tend to get in machine learning. Now, to be fair, this is a model for blood pH. It's very complicated. I suspect some of this detail is not real and should be repressed with regularization, whereas statisticians still learn too simple of a model, but the truth is somewhere in between the two of these is probably the truth. And I think machine learning practitioners tend to be too high variance. And my joke is that statisticians, want to get to the edge of the cliff, but a 95% confidence interval prevents them from getting there. Machine learning people, we're like lemmings. We jump off. We count on cross-validation to sort of save us. And the best place, of course, would be if we both got to the edge of the cliff and had the best view. This is the age plot we get for 30-day readmission. We have patients below age 18. Infants are born into the hospital. It turns out it's qualitatively extremely very similar from age 18 up to about age 80. There are similar jumps for retirement. Retirement now happens a few years later because it's a modern data set. So it's even detected things like that. What's interesting is this is now just blowing up age 0 to 2. It has detected that if you're an infant who's born, you're actually the lowest risk group as a function of age. So it has sort of figured out that being born into the hospital as a healthy infant is actually a very good thing. Okay, so let me show you one interaction. This is a kind of sad interaction. This is age versus having cancer versus not having cancer. And basically, if you don't have cancer, it doesn't really matter. But if you have cancer, surprisingly, it's better to be old than young. And what this has figured out is that these are the typical cancers of the elderly, of middle age and the elderly, which are not that high risk. They're actually fairly treatable today. These are cancers of youth. So these are cancers that happen perhaps in teenage years or younger. You've been treated for years. You're still diagnosed as having cancer, which means you're not considered to have been cured. And unfortunately, now you have pneumonia, which means you're seriously sick. So unfortunately, these patients are very high risk because they have childhood cancers that have been treated but have not responded well to treatment, and now the patient is getting very sick. And the model has figured this out as one of the most important interactions. Okay, so I just want to quickly show you some other terms in the model. The model has learned some surprising things. So it learned, by the way, that having asthma lowers risk, which is exactly what we hoped. And the way we would handle this now it's easy to see this. The way we would handle this is you just zero out this term. You just eliminate that term. Just like it was a rule, you just eliminate it from the graph. And the most important thing is you do not retrain the model. If you retrain the model, if there's any correlation between asthma and other features, the effect will leak into the other features and you won't know it's there. So you just remove this. The interesting thing is it has learned other things like, chronic lung disease, it turns out is good for you. It lowers risk. That doesn't sound right. And it's turns out that, let's see. Sorry. Oh, I'm missing it. It turns out that a history of chest pain is also good for you. So there's 3 terms at least that we would want to remove from the graph. So I just want to show you one other thing, and then we stop. So okay, so this is a model. This is for 30-day readmission. Oh, this is probably the best one. This is a 30-day readmission. This is a patient that has very high probability of readmission, 92%. We've got 4,500 terms in the model, so it's a huge model. And we've just sorted the terms by their contribution to risk. So what makes this patient highest risk? And here are the top 5 terms. It turns out fat emulsions intravenous preparations, so we're giving the patient food intravenously, essentially. The patient has a very bad score for cyclical vomiting syndrome. The patient is receiving amitriptyline preparations, which prevent nausea. They've had a huge number of visits, 64. It turns out the patient's only 2 years old. That's a very large number of visits. And they've been in 18 times in the last 12 months. So their probability of readmitting in the next 30 days is very high. Here's the amazing thing is we've just looked at the top 5 or 6 out of 4,500 terms, and we already have an idea of what's happening with this patient and why they're high risk. They have what's called cyclical vomiting syndrome. That's something that children get, and we're trying aggressively to get food into them. Okay, so let me jump to the summary. Often it's just not ethical or it's impossible to collect the data that you would really want for machine learning. Because of this, accuracy is never enough to deploy a model. You have to somehow understand the model. If you don't do that, you will hurt patients. We've been very lucky. These GA2M models with just single functions and pairwise interactions on healthcare data are giving us as much accuracy as anything else. But the models remain remarkably intelligible. They're not only can we quickly scan them, and doctors can scan them and understand them, but they're easy to edit. We can just remove terms without hurting the model. And it turns out if you really wanted to, a doctor could actually redraw the graph, kind of like a Bayesian model. You could actually redraw the graph. There's very interesting detail in the graphs, which suggests that things that might be causal, but these models are definitely not causal. They're just correlation. So you would have to do further work to try to figure out if the interesting detail in some of the graphs actually is causally true. And these models are really just an example of sort of statistics, pairwise interactions, machine learning, computer science, all coming together. And it'll be useful in other domains as well, because it's always good to understand your model. But we've really been developing, our focus has been to develop these models for healthcare, because we just think it's critical to make sure that the model you deploy is not going to hurt patients for just simple reasons that would be obvious if you could understand the model. So, okay, thank you.
Yeah, just time for one question, one quick question. Yes, please.
Sure. So you have a really nice balance between accuracy and interpretability. And I wondered for you to come a bit closer to the edge of the cliff but not fall over, if your features could be like phenotypes, so slightly more complicated but still very understandable, and that might lead to even simpler and more accurate gas square M or GAM models.
GA2Ms, yeah.
Okay.
It would be very nice to have some extra constraint on the features that are learned, so that they were things like phenotypes or possibly the kinds of things that are learned on the interior of deep models and things like that. If anything, right now, some of our feature shape plots are slightly more complex than we think they should be. So we think we're slightly over the cliff, and we still need to come back a little bit. But that makes sense, right? Because as lemmings, we're already halfway down. We need to come back more. So we think regularization is one of the important next steps. But I agree with you that if there's anything we could do to sort of learn latent, there's no latent features here. If we could learn latent features and then shape those.
So the phenotypes would be latent because they'd be extracted phenotypes. So they would be latent features.
Yes, I agree that would be great.